Thank you for this non-introduction. It's a pleasure to be here. I know that Lausanne is very close to Paris, certainly closer than New York. So I hope to be coming more often while I'm in Paris. So, so what I would like to discuss today is some work on generative modeling with flows and diffusion. And so that's something that started not so long ago with Michael Albergo, who was a PhD student at Grant at the time. In fact, at NYU, he was in physics and has now moved to Harvard. And then Nick Bothy got into play very quickly. He's now at CMU. He was a postdoc. And then there's like, other collaborators, student, postdocs that were all at the Institute. And so that's the work that I'd like to discuss with you a little bit. Okay, so I think for this audience, I probably don't need this slide, but I'll show it anyway. So there's been like in recent years, kind of an explosion in generative AI that allows us now to do things that were thought to be impossible not so long ago. So the few examples that you have on this slide is, and I chose them especially because stability AI and stable diffusion, because they use the technology that I will be discussing later in the talk. But what you can do these days is you can take a prompt that is fairly elaborate and generate images that are consistent with it, and it seems to be realistic. That's one example. You can guess what the prompts are for these images. The screen's a little bit small, but I hope you can see. And then similarly, you can now have an intelligent discussion with your computer. This is Claude Sonnet. I don't know if you can see, but he says, help me prepare a talk on generative AI. And, this is the beginning, and the rest is what you're going to see in the next slides, obviously. Okay. This is using LLM. Recently, this is using the technology I will explain, which is essentially based on diffusion. I'll show that later. This is using LLMs, using transformers, but recently there was an announcement by Inception Labs, probably most of you have seen, where there's a new instantiation of a large language model that is based on diffusion also. Okay, and so what I want to discuss a little bit is, how, what is at the core of these advances. Okay, and okay, so they were essentially, and maybe I'm going too much into introduction for this audience again, but there were two basic advances that created that. One is kind of foundational one, which is to take a probabilistic approach to unsupervised learning. Okay, which is taking as working assumption that the way you're going to organize unlabeled data that come to you, for example, images or text, is by assuming that these data points are sampled from an unknown probability distribution. Okay, that's obviously a big assumption, but if you do this assumption, then you open the possibility to do a generative model, which is that you want to learn this distribution from the data in such a way that you can generate new samples. You want to learn a sampler for this distribution, right? So conceptually, this is quite simple. In 2D, it's very easy to explain what it is. Your data point are the dots that are there, and you want to try to recover what is the distribution that was used to generate them, okay? Which is in this case the levels that are here, and the distribution is there. What makes the problem non-trivial, obviously, is that the data that we are typically interested in, if we want to do images or text, lives in a much higher dimensional space. So, for example, this is a data set of faces, and so we should think about any one of these images or photograph as one data point in RD, which means that D is very large, because if you think about any one of these images, you pixelize it. So say 512 by 512, and then for every pixel, there's a certain number of channels that encodes the information that you have on that pixel. I don't know, 20 channels or something. And so D is 512 times 512 times 30. So you have points like that live in a space that's much larger than this one. So the inference is much more complicated, obviously. Okay. And so how do you do the inference? Well, there's also an old problem, which is density estimation. But obviously traditional methods like histogramming, binning, kernel density estimation, do not scale well in high dimension. Okay, and so that's the place where there's been, you know, big advances in recent years using tools from machine learning, and you know, they were early advanced like Boltzmann machine, variational encoder, GANs. That in fact some of them are being revisited, but the real key breakthrough, I would argue, was when, you know, this was, the problem was formulated as a transportation of measure. And in fact, you know, for example, this is something which was also done by Stable Diffusion. This is based on transportation of measure, and that's the framework that I will discuss right now. So what does it mean? So it's a way where you phrase the problem in the following way, which in fact I know is often called flow or diffusion matching. And the idea is simple, is that you try to construct an SDE or an ODE, like the one that is there, with a drift that is adapted in such a way that if you solve this SDE with an initial condition that is drawn from a sample base distribution or base measure, like for example for a Gaussian, you could think, then at time t equal 1, the solution will be a sample from the target. Okay. So this is a dynamical transport of measure. We know mathematically a lot about this problem. In particular, we know condition on the measures that guarantee existence of a drift that will achieve this feat. And the main practical question is how to construct it from the data, right? And obviously, if you can do that, this is well suited for generation and sampling because, well, by definition or by construction, drawing the initial condition is easy. Solving the SDE is also easy to the extent that we have good integrators to perform this task. And so you can easily, by these two operations, get sample from the target. Okay, and this is illustrating, which was a movie, what's happening. So this is a drift that has been learned by a technique that I will be discussing in a minute, where at one end you have like the noise, which is like, you know, the pixels are just drawn randomly. And then there's a drift that has been learned that actually generate images where the drift was learned by using a data set which is called the FLAIR data set. And so what you get here are fake flowers. Okay. So there was a breakthrough, right? Okay, so, and again, this is something I should maybe say. So the question is really, you know, how to learn the B, which if we want to do machine learning, essentially means how do you find a tractable variational formulation for this B? Okay, because if you have that, what does that mean? That means you want to have a loss for B that you can evaluate on the data. And if you can do that, then you can, you can approximate B by a large deep neural network. And you can estimate the loss by empirically over the data, and then you can do stochastic gradient descent to adjust the parameters. So that's the thing. Okay. So a breakthrough in this area, the first one, which is not so long ago, was in fact this idea of noising, denoising, that really started with this paper by Saul Dickinson in 2015. But the version that really, you know, that is the blog here is the paper by Song and Ehrman, which is from 2021. Don't remember if it was an idea. What they had as an idea is the following. It's quite simple again conceptually, is that you take your data and then you noise them. The way you do that specifically is by using an SDE. Okay, think of an ocean and back process, for example. So that's an SDE which has the property that its invariant measure is a simple Gaussian, an N01. And so you take your data, you noise it. So going this way is very easy. And you have the data for every data point here. You can have a collection or a sequence of data that correspond to noising that images. And then you can use result from stochastic process theory that says that you can time reverse this diffusion process or this Markov process, meaning that you can go in, this is not anti-diffusion, it's time reverse diffusion, so you can go in this direction. And what you need to know in order to do that is you need to know the score, which is the grade of the log of the probability density function of this process, time dependent. Okay. If you know the score, then you can turn noise into data. Right. And really what they showed is that this can be done by regression. And that was the breakthrough, because regression is simple on the data. You could learn it. Okay, and that was building on other result by Eijnden and Vincent that shows how to learn the score. Okay, and this was really the breakthrough. So I'm going to go back to this towards the middle of the talk, but what I'm going to now explain is essentially a method that we introduced that is based on a similar principle, but in a way is simpler. So I'll first describe that, and then I'll go back to explain the diffusion processes. So what I want to discuss is stochastic interpolant, which is something that was introduced with Michael Albergo in this paper. There were two papers in the same issue of iClear that propose essentially the same idea, one by Lipman and Chen and others that called flow matching, and the other one by Liu and that is called rectified flow. Okay. And so the idea is actually very simple, is that you introduce, so the idea is that we're going to create a bridge between two distributions, and we're going to do that at the level of the samples, assuming that we have access to sample on both. Okay. And the way we do that is by introducing this stochastic interpolant, which is a stochastic process which is written there, where, so it's a linear combination of a data point that is from a base distribution, a data point which is from the data distribution we're interested in, and then some latent variable that I will the role of which will become clear in a minute. Okay. These two guys can be coupled, but this one needs to be independent of the other two. And then there are time-dependent coefficients. That's why it's a time-dependent process. These alpha, beta, and gamma, which are time differentiable function, which you adjust in such a way that they satisfy specific boundary conditions, which are written there, which guarantee that if you evaluate this process at time t equals 0, you get x0, and if you evaluate at time t equals 1, you get x1. So, for example, you could think about this choice here, and you could think about drawing x0 and x1 independently from the base and the target distribution. Okay? And so what this does, right, so by definition, you have this, and if you have access to data and you can draw Gaussian, you can sample this process very easily at any time t equals 1, right? So the way you could think about this is like this: is that you take, imagine, so this is a cartoon, but imagine that this is the base distribution, which is this, doesn't need to be Gaussian, it's just this double moon distribution, and let's imagine that at that end you have like this checkerboard distribution. What you do is that you take points, you draw point randomly here, you draw point randomly here, and then you pair them randomly. Okay, and then if you do that for clouds of point, what that gives you is an interpolation in sample space, which of course induces an interpolation in measure space between the two. That's what the cartoon is here. There's another little movie that shows this maybe a little bit better, which is, so this is a pairing of the points. And then it just shows you, if you take t equals 0, 1, how this cloud of point move from one distribution to the other. Right? Okay. So a few remarks, is that...
Sorry. Is it a pairing or x0 and x1 are sampled independently?
You can do it independently, you don't have to. I'll get to that later. Okay, as long as the marginal, so you can use a distribution which is a joint distribution of x0, x1, as long as the marginal gives you the target and the base you're interested in, you're good. And pairing can be useful. I'll get to that in a minute. Okay.
Interpolant linked to the Wasserstein geodesic kind of an idea.
I'll get to that. No, it's not the way. So I should have mentioned that maybe in one of the previous slides. What you're interested in here is a transport of a measure to another, not necessarily the one that is optimal in the sense of Mont-Jean-Père, Canterbury. Okay, I'll get to that in a minute. Though there is a property of this interpolant. It's not optimal, but it has a good property in that sense. Okay, so notice that this is not necessarily a diffusion. You could, choose this guy in such a way that it has the law of a Brownian bridge, but you don't have to. Notice that the base and the target you don't need to have that the base is Gaussian. You can, for example, go from the data set to itself if you want, right? And x0 and x1 can be correlated. And then notice also that there's a choice of design here, which is that you can choose your coefficient alpha, beta, and gamma in different ways to get different interpolation. This is one where there is no latent variable. There's a little bit of latent variable. This is a case where you devolve everything into noise and then back into the data.
The slides I was going to be talking about.
Oh, okay. So yeah, right. Yeah. Okay. Sorry. Feel free, but without the notes. Okay. So there's a very simple result that you can prove, namely that if you look at the law of this interpolant at any given time, is the same as the law of the solution of an ODE, provided that the drift is given by the conditional expectation of the time derivative of the interpolant at conditional on the interpolant going through x. So in other words, if you look at the interpolant, you can calculate what is the I dot at a given point. There will be many of them. And if you take the average of all of these velocities, you get that drift. Okay? And this conditional expectation can be represented in variational form using the L2 formulation of conditional expectation as the minimization of this loss. Okay? So the proof of this is sufficiently elementary that I can flash it by you very quickly. If you take, if mu t is the distribution of IT and you take a test function, well, by definition, that means that this mu t is such that if you take expectation against mu t, you get the expectation over the interpolant. And then what you do is that you take the time derivative of these expressions using chain rule. And then simply you use the Tower property of the conditional expectation to arrive at a transport equation, whose characteristics is simply this ODE. And that's the end. Of course, I mean, if you want to make this rigorous, you need to guarantees that all of these objects make sense, but essentially that's the proof. Okay. And so what this gives is a generative model now, because to sample the interpolant, you need data. So it's not a generative model. But to solve this as these ODE here, you just need an initial condition that you can draw from the base. And then you just, if you know the drift, you push it and you get the target. Okay, right, this is a little illustration on a one-dimensional example that go from a Gaussian to a Gaussian mixture. In fact, this flow is the actual flow that you would learn in that case. Okay, notice that the interpolant in 1D would, if you pair these guys independently, all the rays are crossing. But once you have learned the B, because it's a vector field, now the flow lines are much more regular. Right? So these are the flow lines that we get in that case. And the property that you have with this B is that if you sample at that end, you push it, you get sample at the other end of the target distribution. Okay? And there was a question about the optimality of the transport. It's not optimal transport, but you can bound the Wasserstein distance very easily with property of the interpolant. Okay, which is much more complicated to do with other technique that, for example, we do the interpolation not in sample space, but directly in measure space. I think this is what you get. Okay, and so now we're in business because, well, first of all, we can compound all of these. This loss here allows you to learn the drift for every t. You can compound it by integrating in t, and then you can think about this integral in time as an expectation over uniformly distributed time. And so that means that you can, estimate this expectation here fairly easily since you have access to the data, right? You just need to draw a triple where you would have an x0, an x1, a z, and a t that are from the base, the target, the Gaussian, and the uniform, respectively. And for every one of these quadruple, you have a point, and then you take a mini batch of that, and you estimate your loss here. And then if you do that, that means that you can, in principle, do stochastic gradient descent over this objective, and you do the what over the parameters of the deep neural network that you use to represent the B. And I'm not going to go so much into the detail of that, but the result that I'll show you before were done using U-nets or transformer for the drift. This drift has the same dimensionality as the score, so we can use all the architecture that the people in score-based diffusion have been using to do this optimization.
Small question.
Yeah.
What are you regressing the drift over? The B hat of IT minus what's the?
This is I dot. This is the time derivative. Right, so you're regressing the B, which is the velocity field for the X, over the velocity field of the interpolant, which is the I. And the reason is that the minimizer of this objective is the conditional expectation.
I in alpha and beta and gamma chosen a priori, or you're also trying to...
You choose them a priori. Right? For the rest of the talk, you could imagine that this is 1 minus t, this is t, and this is something, this is t times 1 minus t or the square root of that. Okay? There is flexibility of design, but right, but you can do that.
So all of this hinges on the fact that initially you start with some distribution, in the end you end with some other distribution. Does it mean the flow is weak like this?
The flow is, I mean, if you ask, is there a way to transport this measure to the other one in a way which is different from this drift? Yes. But what is important here is that once you have fixed the interpolant, then no. That actually fixes the transport. Because once you fix the parameters gamma, beta, and alpha there, and possibly the coupling between x0 and x1, that means that you have fixed the mu t, the time-dependent distribution of that object, and what you're tracking is that. Okay? That, in fact, is what makes the problem tractable. Because you create a bridge, you fix a bridge in distribution space, and then you regress upon it. It's a bit of a technical comment, but there were earlier methods where you could try to learn an ODE like that using the neural ODE framework, for example, in which you could use as a loss simply the fact that the cross entropy of the push forward by this ODE of the base towards the target. If you do that, you don't fix any path. You're just looking at the target. And so in principle, it looks like it's easier a priori, but in fact, it makes the problem much more complicated because the optimization is much more complicated because you now need to do backprop through the solution of the ODE to do the optimization. There's an adjoint problem that you need to solve. Here, there is no adjoint problem. It's really a quadratic regression that you can do on every time slice. Why? Because you have fixed the path. Okay. I think accelerate a little bit. Okay, so the title was flow and diffusion. I have shown you the flow, which is the ODE, this probability flow ODE. Why do we introduce this latent variable z? Is because you can then use Stein identity to calculate the score, which is the gradient of the log of the probability, time-dependent probability. Okay, this is a well-known identity. In fact, if x0 was a Gaussian independent of x1, you would not need this latent variable. It's only used in the case where you would have things that are correlated, and then you want to have a latent variable that's independent to be able to use Stein identity. So you can learn the score by optimization. And then if you have that, there's something which is interesting that you can do, namely that you can use in some sense a trivial identity, which is, and I realize that is very small, but it says that if you take the divergence of the score times mu, that's the Laplacian of mu. Okay? And so that means that the transport equation that we had before, which was without this term and without that term, which is just the transport over the drift, you can now modify it by adding a diffusion term on the right-hand side and the compensating drift on the left-hand side. At the level of the equation for mu, these equations are all identical because you could cross this term and cross that term. And this is true for any epsilon t that's positive. What's the advantage of doing this is that even though at the level of this distribution, this is the same thing, you can realize now at the level of the path differently, because now you can read an SDE out of this. So these are the SDE. Okay, so you have a family of SDEs in which you can adjust the epsilon t, which is the diffusion coefficient, post-training to do the sampling. Okay? Okay, so let me summarize that and then move on with example. Right, so what's being done here is like you have, so suppose that you want to go from this base to this target. You can choose, give me 1 second. You can choose an interpolant that will give you the way you interpolate. Okay, this is just a family of distribution that move from there to there. And it's done with this interpolant by choosing the alpha, beta, gamma. Once this is fixed, you can learn the score and the drift. And once you have learned the score and the drift, you can sample these guys differently. So this path is the one that is here, the one is there, and so on. And this is what you have if you sample with the ODE. And this is what happens if you take SDEs with different values of noise. There was a question.
Just to make sure, so how do you estimate the score? Because you had it as an expectation conditional of IT equals X.
Same thing. Similar thing as before. This is a conditional expectation, but the conditional expectation you can always write down as in L2 formulation as the minimizer of a quadratic loss. Okay. In fact, and I'm going to discuss that later, you don't even need to do this optimization in simpler case where the latent variable is equal to 0, x0 is Gaussian, you can deduce the score from the drift. So there's only one quantity you need to learn. But otherwise you just do two optimizations, two neural networks. Okay. Okay. So another little illustration of this, if for the FLAIR data set, this is the same noise, the same draw of x0, and then you pass it through the ODE or through the SDE that you have learned with different value of epsilon, and then what you get is different flowers. In this case, if you take this noise, you will always end up to this flower. In this case, because there is noise, if you take that guy, this x0, and you push it because there is no an SDE, you can get different flowers. And same thing with variability here. Okay. A little remark, which is kind of, you know, the magic of neural network a bit and their mystery as well. If you take this generated image, you could ask yourself, have you memorized the data set? And the answer is no, because if you look in the data set, which are the 5 closest images, here they are. You need a metric to decide which is the closest. This is just standard metric in L2 in the embedding space that is being used, which is the pixel space. And you see that this guy has features of each of those, but it's not any one of them. So it's the remarkable fact that it does generalize into creating new flowers. Okay. Why would you want to use the SDE over the ODE? It's because you can, using Girsanov theorem, you can prove a simple bound on the Kullback-Leibler divergence of the true target from the one that is generated if you use an imperfect drift and an imperfect score. Right? Remember, all of this relies on estimation. In general, you will not be able to calculate exactly the drift and the score because you have finite amount of data, because the expressivity of your network is finite, and because you don't optimize fully. But you can quantify the error, and the error, in terms of the KL, is expressible in terms of the loss, in a way which is not completely constructive because you don't know what is the minimum value of these losses, but still you have this expression. And so that tells you, this is in the case where epsilon doesn't depend on time. And so this is a very simple consequence of Girsanov theorem. In fact, this is inequality at path level. If you look at the path KL, that bound, you know, by the disintegration property, bound the KL at the finite time. And so this tells you that in principle, knowing, if you were to know what this guy is and what this guy is, there is an optimal value of the diffusion coefficient. Okay, so you can adjust post-training the diffusion coefficient that you use in such a way that you will limit the impact of the estimation error over the generation error. Okay, and you can actually check this. Just look at this curve, forget about this one, it's another estimation. This is epsilon, and this is the KL that is estimated for a Gaussian mixture in 128 dimensions. Here you see slice, and you see that this KL bond is actually realized in the sense that there is an optimum epsilon somewhere over here for which you have the best estimation error given best generation ever given the estimation error that is inherent to the learning in that example. Okay. Okay. I said that already, so don't need to repeat. Okay, let me go back to diffusion model, to make the connection, because it looks like what they discussed is very separated, but let's see. So remember what I said for diffusion model, right, is that you noise, you denoise. Okay? So as I say, this was, I think, a fundamental breakthrough, these ideas, but there's something a little bit annoying about them, or not annoying, but a bit limitative, is that the base distribution is always a Gaussian, because you always noise towards the Gaussian. And there's also the thing that there's a time t here that needs to be taken sufficiently large, because when you noise, it's only at time t equal infinity that this becomes a Gaussian. So if you don't go all the way to infinity, which in practice you have to do, and you draw a Gaussian here, you introduce a little bias. That's minimal because it's exponential. But the point I want to make is the connection. So suppose that you do this diffusion in a time tau, and the reason that I write this time as a different time is, so suppose I use an Ocean-Beck process to pass this data point. So this is what this SDE is. Okay? It starts from the data, it goes from the noise. So this Ocean-Beck can be solved very easily. And in law, the solution is simply this, which exactly tells you what is that the noisy sample that you have here is the original sample that you have fade out exponentially, and then you add exponentially fast some noise onto it, right? And now notice the following thing, which is that if you change the time by taking t equal e to the minus tau, that reverse time, remember in my case, the data was always at t equal 1, and the noise was at t equals 0. So this reverse time, and it also maps infinity onto 0 and 0 into 1. And so in terms of this new time, this process is just this interpolant. And so this is, you recover that just by a specific choice of alpha and beta, and without latent variable, with the fact that, in fact, the latent variable here is that guy, or if you will, I mean, there's no x0, there's no z, the way you want to think about it. Okay, so that's the way you connect with diffusion. Now, that's important because what does it say? It says that, and maybe this is the one thing that we have learned by this stochastic interpolant, is that what this process of noising, denoising did is in fact mix two operations that should be thought about conceptually as independent. One is creating the time-dependent mu-t that connects the data to this, so the data distribution to the base distribution. And you can do that with any base distribution, as I've explained before, okay? And then that is what allows you to do the regression of a drift and a score. But once you have done that, the sampling of this distribution by the SDE ODE doesn't need to be done by reversing, the process that is being done. You can do it in any way you want once you have the drift and the diffusion at your disposal, including by adjusting the diffusion coefficient. Okay? And I think this realization is important because that's a conceptual leap that shows you that there is much more flexibility into these type of methods that what you might think of if you just think about this picture. Okay, let me give you some applications. Yeah.
Just to be sure I understand. So you discussed the Ornstein-Uhlenbeck, but in the diffusion model, the SDE is much more complicated.
What they do typically is that they put a time-dependent G here and a time-dependent G there, which is just a time rescaling of this. Okay, and then there's another instance. This is what's called variance preserving. There's also what they call variance exploding, where in fact you don't put this, you just put that guy, right? And then the whole thing kind of grows. And then what you get is that there's another form of bias in that case, that if you cap at a certain t, you still have the data somewhat embedded in it, but a small part is the same. Okay, I took this one. You could put the GT here like they do. I took this one because it shows that if you go into stochastic interpolant, you can actually remove completely with this conceptual, this change of variable, you can completely remove the bias from the finite t here. Okay. Yeah. Okay, some application. The first one, this is a little bit of propaganda, so it's just that these methods are scalable. like, with a colleague at NYU, Seining Che, who had introduced what he called diffusion transformer. He used diffusion architecture, so transform architecture to represent the velocity field. And this is the kind of images that you can generate on this is, these are fake images. Okay. And this technology is now, as I say, the flow matching stochastic interval rectified flow was now being used with stable diffusion, the image generator that is being used by Meta and other because of flexibility. Okay, and this is just in-house calculation. So of course, if you go to the website of this company, you'll see things that are much more impressive. But okay, we could do it. Okay, so I explained to you that there's flexibility. So all of what I'm explaining here, if you tweak things and you think about, you can also do it with diffusion. But it's easier to think about them directly with the framework that I showed you. So here's a few tasks that I will flash by you. Suppose that you want to do super resolution or denoising. You have pairs of images that where you have in your training data set, you have a full resolution image, say, and a low resolution image, noise, or but it's been noise in some sense. Okay. So in this case, what the task is, you'd like to train your model so that at generation stage, you give this and you kind of denoise that image. So it's kind of clear here that it's easier to think about this by saying, this is my target distribution. This is a sample of my target. This is a sample from my base. Okay, I don't need to go to Gaussian. I need to go there. And they are paired. Because if you're training data set, you know that this is the bird whose noisy image is that one. It would be stupid to reshuffle things at that end compared to that one. Okay, so this is a very simple example that shows that having the flexibility to have paired data and to go from a base that is non-Gaussian towards your target is easy. So that's what was done here. And in fact, what you see here is something which is not on the training. This is on test set. So this after training, this is the kind of image that you can get, and then it's compared to this. It's a generative model. So, of course, you cannot get the truth. Same thing here. Here's another task. I don't think I need to explain. It's the same idea. Is you need to unmask, right, or in-paint things. And so here, again, the base is the set of masked images that are paired or coupled to the set of unmasked image. The masks are random, and then you can use all the flexibility to say that the velocity field needs to only be non-zero where the masks are. And then in this example, the masks are random, but you assume that you know where they are. So at training stage, you get that information. You also give the information at generation stage. This is the kind of image that you can, recover. Okay. There are interesting things that occur if you do this, like this, which is, this is one generation of a dog so this again is a generation stage. This was the masked image that was given. This is the one that is generated. This was the one that was in the data set. Okay. And you see that, well, there is one striking difference is that this dog has its eyes closed. But obviously, this is an hallucination that is not completely stupid in the sense that you can't tell that the eye was closed or open from that. Okay. If you look at it closely, you'll see that the eye is a bit flat. But okay, but again, this is in-house calculation. Okay. How much time do I have? 5 minutes? 10 minutes? 10-ish. 10-ish. Okay. So let me. Okay. So there's a very simple tweak to this that allows you to do tasks that are a little bit more sophisticated. In fact, the previous example could also done with this, namely that you can do conditional generation. So suppose that what you have, let's think mostly about the data, is that the data is paired in the sense that you have, the data point that you're interested in, and then some conditional variable. Okay, so you can think about this triple or just these two as being joined from, drawn from a joint distribution like this. Right? So, okay, I'll give you an example in a minute. And then what you would like to do is that you would like to draw samples that are from the distribution marginalized on X1 and Xi, and then condition on Xi. You're going to do conditional generation given, and I'll give you an example in a minute why that's useful. The formalism is exactly the same. You just need to do regression by using paired data and including an extra argument in the velocity field, and as a result in the score, that is the conditioning variable. So at training stage, you just train things like this by using these pairs that define what the IT is. You obtain that, and then at generation stage, if you're not given the conditioning variable you're interested in, you want to draw the target distribution with this condition given, you just include it as extra argument in the velocity in the score, and that gives you the conditional generation. It's super simple. And this is not new, in fact. This is very much used, by everybody doing diffusion. So I'm going to explain to you this is useful to do forecasting or downscaling. So suppose that you have a time series, and what you'd like that you use for training. And so what you'd like to do is that you'd like to calculate the probability density function of the state of the system after a given lag, given some full or partial information about the state of the system at the previous lag. Okay, so this is the conditioning variable, and this is the x1 that you want to predict. Okay, so here is a little example that demonstrates what this does. You take a movie, and then the conditioning variable that you use is a few frames from the past, and what you want to generate is the next frame. Okay, and then if you do that, you can actually do rollout, which is that once you have generated that, then you say, well, let's do forecast over the forecast. Okay, so this is movie generation in an auto-regressive way, which is different from what is done, for example, in Sora, right? And this is an example of the original movie and then a movie that is being generated with this type of method, and another example there. It is maybe easier to look at them with little movies because again, this is done in a latent space. So you embed and decode, and there's a lot of work that goes into that. But there's something which is quite remarkable in these things, which is that, so this is the original movie in each case, and these are movies that are being generated by rollout, where you forecast the forecast. And you can see that they're all different because it's probabilistic generation, right? Each time you do it, you get something which is different. But you see that these movies are not completely crazy, which is sort of remarkable. The physics seems to be preserved, even though it was never inputted. It was learned from the data. You don't, they don't do complete. If you look very closely, you'll see a few strange things. Okay, there are physicists in the audience. They can, pin me down on this one, but it is sort of remarkable. And you see that they are different. Like they're okay. There are other things that you can do with this. So this is the solution of Navier-Stokes equation in 2D. I'm showing you the vorticity field. The equations are there. There are stochastic differential equation with a random forcing. I don't have time to explain to you what that is, but essentially this is the vorticity field of a turbulent fluid, if you wish. And we choose a setup in which we know that there's an invariant measure. So you can generate by simulation a time series of this, which is ergodic with respect to an invariant measure that you don't know. Okay, and then the task that you have to do here is that if you give yourself the vorticity field at some time in low resolution, say, you would like to predict what is the vorticity field at a later time in high resolution, right? And this works. You can actually do it. It shows you why it's useful to have probabilistic forecasting, because this is one. So this is the low resolution data that allows you to generate this high resolution data at a later time. So what you can do is that you can do this generation, create this ensemble, and then compute this conditional mean that you can compare to the conditional mean the truth. And you see that since it captures the ensemble, it also captures the conditional mean. But it's telling you that if you were to do regression on the conditional mean, the information that you would get is fairly limited. I'll get back to this point in a second. Okay? So this contains the information that is here, but this doesn't contain that information. Looking at problems from physics is kind of useful, and I'll elaborate a little bit on that at the very end of the talk, which is pretty much now, which is that we know certain things about these systems. For example, is Navier-Stokes equation. So there's a spectrum of the entropy that you can calculate. You could also do that for image, by the way, but this is the spectrum in blue. Okay, the entropy is being inputted here, and there's dissipation. This size of the box, and this is where there's the viscosity. And so, of course, if you calculate the spectrum of this, you don't have any information past a certain, this is wave numbers, past, high wave number, which is small scale since it's low resolution. But what you can check, and of course, this is a condition which is, necessary for accuracy, but not sufficient, is that you can calculate the spectrum of your generator, right? And check that it fits the spectrum of the target, which it does. Right? So this is not just pretty images, these are pretty images that have the right entropy spectrum, which is okay. So these things are being used, or similar ideas, by Google in GenCast and by NVIDIA to do weather forecasting, which is again an instance where you don't necessarily want to regress on the mean, but you really want to compute the ensemble of forecasts. Right? If it's, tomorrow it could be sunny in Lausanne and cloudy in Evian, or the other way around. If you compute the mean of these two states, you're going to get a weather that is observed nowhere. You'd like to know the probability. Okay, I'm out of time. I wanted to discuss a few generalizations, but I think there's too much background, but I'll just flash them by you, and I can discuss that offline with anyone who wants. But the ability to calculate the score allows you to do non-equivalent statistical mechanics. Because fundamentally what I explain is that when you calculate the score, you can time reverse the dynamics of diffusion. Okay? And so in non-equivalent statistical mechanics, one of the main questions that is being asked is, what's the arrow of time? Is there entropy production? Okay? I'm not going to show you these are non-equivalent. Okay, so let me maybe just explain this and give you one more slide of background. The movie that are there. Do I have a minute? Okay, so let me see if I can play them. Are they playing? Right. So these are interacting particles. These interacting particles repel. Okay, but there is an active force that is being put on them, which is that they tend to swim in one direction. And so they might collide. And when they collide, they keep stubbornly to want to go in the direction that they want to swim. And this is only varying very slowly. Okay, there's a latent time. So what this can create is a gigantic traffic jam, which is a phase transition. Okay? This is a non-equivalent phase transition because it's driven by these active forces. If there were no active forces, you would not obtain this traffic jam, because since they repel, they would just be a gas where they all try to be away from one another. Okay? Now, there's a lot of background about non-equivalent statistical mechanics, but fundamentally the question that you could ask is the following. Am I showing you this movie played forward in time or backward in time? Okay? And it's not so easy to tell. If the system was at equilibrium, there would be no statistical test that allows you to tell whether you go forward or backward. But active system, you can't tell a priori. So how could you tell? Well, this has been debated, that there's the framework that has been discussed for that. These frameworks are quite complicated because if you want to time reverse things, you need to learn the score. 5 years ago, 10 years ago, people would have said, well, okay, forget it, like it's impossible. But no, we can. Okay, using this score-based diffusion model. So if you take this system and you calculate the score, which is the score of the probability density, of the joint probability density function of all of these particles, you can actually figure out where, what they do is different forward and backward in time. And you can quantify entropy production. The same thing, this is another example that is famous, which is this so it's a Vishek. These are flocks. It's a model for flocks of birds, where what they do is that these little swimmer, they do essentially it's an oceanic motion, except that the velocity field that they have tend to align their velocity if they're close. It's a model for flock of birds. And so you could ask yourself again, is this shown forward or backward in time? If you reverse the arrow and you play it in the other direction, do you see a difference? And here you can use these tools to quantify the fact that there's entropic production or consumption when the flock breaks or form, and you can calculate its statistics, etc. I mean, this is really something I can discuss offline with with whoever is interested. Okay. Now, 2 more minutes. You can also do this to assist Monte Carlo sampling. Okay. So far, I have talked about a sampling which is sort of a bizarre sampling from the viewpoint of people that do Bayesian inference or statistical mechanics, because the sampling in which you're given the samples. But typically the problem is that what you're given is a model, like a Gibbs distribution. You want to sample it, you don't have samples to begin with. That's done with Monte Carlo. And this is applied to many instances. So in principle, right? So these methods are hard because they're always based on the fact that you can't sample directly your target distribution. So you make proposal moves, and then you unbias from another distribution, which is simpler to sample, and then you unbias it, either by doing importance sampling or by doing metropolis R-state. And the conversions, meaning the effective sample size that you have after having generated n samples, is typically much smaller than the number of samples that you have generated, because it's hard to generate good samples. And so when you unbias, you kill the quality. Either the conversion rate of the Markov chain is very slow, or the importance rate has very high variance. Either way, your effective sample size could be dramatically smaller than the number of samples you have generated. Okay, so you say, haha, very easy. We can use generative models to learn or to generate better samples. And there's a lot of paper that they've been, that's starting, and it's really exploding right now. The idea is you use the data to generate new samples, right? You use the data to learn a generative model that will allow you to generate better data, and then there's a feedback loop on this. Okay, and so I think it's a very interesting thing. We are working on this. There is a curse and a blessing in this problem, and I probably will leave you on, with that, which is that these are problems with model but no data initially. So they are harder. That's the curse, because typically in fact, they will not be solvable unless you have a warm start, at least a few samples. But they have one thing that is very, there's a blessing which is very different from what you have when you do data science, like images, is that you can generate infinitely many data because you can validate them. You can compute this importance weight, or you can accept rejected metropolis, meaning that you have access to infinite amount of data with these methods a priori. So that's, verifiable AI. With images, it's very difficult to verify what you do, but here you can. Okay. Yeah, I have a slide about the fact that, but this is another talk, which is that for the moment, all of this talk was, working in suspension of disbelief. Namely, we are learning, velocity fields or scores in very high dimension. And again, I mean, if I had shown this talk like 5 or 10 years ago, like people would have walked out because it would have, sound like lunacy. You can't do this thing in high dimension. Why? Because there's the curse of dimensionality, which says that the cost of making calculation increase exponentially with dimension. It's essentially saying you can't grid space. This term was coined by Bellman in 61, so no problem. Okay? Just to fix ID, I know this is trivial, but if you take 2 grid points in 1 dimension, that's 4 in 2, but this is, 10 to the 300 points in 1,000 dimensions. The images that you saw is a much higher dimensional space, and 2 grid points per dimension is a very small gridding of space. So there is a question as why the hell is this possible to do? Okay, and so is this question clearly? It means that the data needs to have some structure. The effective dimension cannot be the one that you think it is, because otherwise it would not be possible. But how so, and what does that exactly mean? The very vague statement that I made is in fact an interesting, problem. Okay, and then I have my little slides, need for theory, which is that's really I'm really at the end. All of these advances rely on these neural networks. These neural networks are fantastic, but they are very costly. This is the way performance increases as you increase the number of data sets. This is logarithmic, so it will be pretty bad, unfortunately. And then this is the, you know, the killing of the planet by deep learning. This is the amount of compute that is being necessary to do these calculation when you use AlphaGo or ChatGPT. This is exponential. This is 4 times per year. This much faster exponential growth than most. Okay, it's not really sustainable. And right now we need to do that. The image that I showed that were generated, this is what happens if you don't use sufficiently high networks. You generate images. It's kind of interesting because you generate kind of ghosts of images that only emerge if the network is sufficiently high in size during training. Okay, they're like steps. Okay. And that's all I had for you today. Thank you.